Right now, an entire world is finishing a complete 4-season calendar year before you can even finish a single game of football. While you sit in your chair, a real planet in our galaxy is blasting across thousands of miles of empty space, rushing through winter, spring, summer, and fall in less time than a regular school morning. It does not wait 365 days like Earth does. It completes its entire journey around its home star in just a few short hours, defying the traditional laws of science we were all taught in school. If you enjoy uncovering the strangest, most mind-bending mysteries of our universe with plain and honest facts, take a second right now to subscribe and become part of our growing community of curious space explorers. For hundreds of years, astronomers believed that planets in our universe had to follow very strict rules about how fast they could move. In our own solar system, Earth takes 12 full months to travel once around our sun. Mercury is the closest planet to the sun in our neighborhood. Yet it still needs about 88 full days just to finish a single trip around its orbit. Because of this slow and steady pace, scientists wrote in textbooks that no world could ever survive spinning around a star much faster than that without getting ripped to shreds by gravity. Every computer model built by astronomers in the 20th century suggested that a planet needed a lot of empty space to grow and survive. If a giant ball of rock or gas formed too close to a blazing star, the immense heat would boil its air away, and the intense gravity would tear it into tiny pieces. For decades, researchers assumed that every planetary system in the galaxy would look roughly like our own, with small rocky worlds tucked safely near the center, and massive gas giants floating comfortably far away in the cold outer regions. That safe and comfortable assumption completely shattered when powerful new instruments started staring deep into the void of our Milky Way galaxy. In 1995, 2 Swiss astronomers pointed an observatory in southern France toward a star 50 light-years away called 51 Pegasi. What they found shocked the entire scientific community to its core, because they detected a giant planet the size of Jupiter orbiting its host star in just 4 Earth days. Nobody had ever imagined that a giant ball of gas could survive that close to a raging stellar furnace without evaporating into nothingness. That single discovery opened the floodgates for a brand new field of astronomy called the search for exoplanets, which are simply planets that orbit stars outside our own solar system. Suddenly, researchers realized the universe did not care about human textbooks, or the neat rules we invented based only on our own quiet solar system. Over the next 2 decades, massive space missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, known as TESS, began searching thousands of distant stars. These telescopes watched for tiny dips in starlight that happen whenever an orbiting world passes directly between its star and our cameras. As the data poured back to Earth, astronomers began finding stranger and stranger worlds that pushed the laws of physics to their absolute limits. First, they found planets with years that lasted only 3 or 4 days, which seemed completely wild to researchers at the time. Then, they discovered scorched worlds where a full year took just 24 hours, meaning an entire orbital cycle happened between one sunrise and the next on Earth. But deep within the constellation of Puppies, roughly 860 light-years away from our planet, astronomers spotted something that seemed physically impossible: an exoplanet named WASP-19b. WASP-19b is a massive gas giant, slightly heavier than Jupiter, but it orbits its parent star at a distance of barely 1.2 million miles. To put that in perspective, Earth is 93 million miles away from the Sun, while the Moon is about 240,000 miles away from us. That means this gargantuan alien world is skimming just a tiny fraction of space above the bubbling nuclear surface of its star, racing around it in only 19 hours. Astronomers initially thought this 19-hour orbit was the absolute limit for how fast a massive world could travel without being shredded by gravity. They believed that anything moving faster or orbiting closer would instantly crash into the star or turn into a giant ring of dust. But then, an international team of scientists pointed their instruments toward a small, dim red dwarf star named TOI 561, located hundreds of light-years away. What they uncovered next redefined everything we know about how fast a world can move through deep space. They detected a small, ultra-dense, rocky super-Earth, now cataloged as TOI 561b, that circles its star in an unbelievable 10.5 hours. Before you even finish a normal 8-hour workday and commute home, this rocky planet has experienced 2 entirely separate New Years. Have you ever imagined living on a planet where your birthday happens twice in a single day? Or did you think Earth was the standard for how the universe works? Leave a comment below with your thoughts on how bizarre this is, and hit that thumbs up button to help more people discover these cosmic anomalies. To understand why these ultra-short period planets exist, we have to look closely at how gravity actually works in extreme environments. When a planet gets pulled closer to a massive star, the star's gravity grabs hold of it like an invisible cosmic leash. The closer the planet falls toward the center of gravity, the faster it must travel in its orbit to avoid falling straight into the star's fiery heart. Think of it like spinning a weight tied to the end of a string around your hand. If the string is long, you can swing the weight slowly in wide, lazy circles. But if you pull the string very tight, so the weight is only a few inches from your fingers, you have to spin your hand with incredible speed just to keep the weight moving smoothly through the air. These ultra-short period worlds are traveling through space at mind-boggling speeds of several 100,000 miles per hour. Earth moves along its orbit at about 67,000 miles per hour, which feels fast until you compare it to a world like a TWI 561b. That rocky planet is blasting through the vacuum at more than 3 times the speed of Earth, enduring violent forces that would easily rip our own world apart. Yet, speed is only half of the mystery that keeps scientists awake at night. When an exoplanet orbits this close to a star, a phenomenon called tidal locking takes place almost immediately. Tidal locking happens when the intense gravitational pull of a star slows down the planet's daily spin until the exact same side of the planet permanently faces the star at all times. This means these planets do not have normal days and nights that cycle with morning, noon, and evening. Instead, one half of the world is locked in permanent, blinding, eternal daylight, while the other half is frozen in endless, pitch-black night. The side facing the star becomes a raging sea of molten rock, where surface temperatures can easily climb above 4,000 degrees Fahrenheit, hot enough to melt solid iron and turn rocks into vapor. On the permanent night side, however, temperatures drop drastically, creating a violent clash between extreme heat and freezing cold. This insane difference in temperature generates global winds that blow across the planet at thousands of miles per hour, faster than the speed of sound. These planetary storms sweep vaporized rock from the daylight side toward the dark side, where the mineral vapors cool down, condense into liquid drops, and fall from the sky as literal molten lava rain. Scientists originally thought that no atmosphere could survive this level of constant radiation and heat. They predicted that the powerful solar winds blasting from the host star would strip away every single molecule of gas within a few million years, leaving behind a naked, barren rock. Yet, when the James Webb Space Telescope recently aimed its ultra-sensitive infrared cameras at some of these close-in worlds, it revealed something completely unexpected. The telescope detected thick, glowing envelopes of heavy chemical elements lingering around their upper atmospheres. Instead of having light gases like hydrogen and helium, which were blown away long ago, these planets are actually creating new atmospheres from the inside out. Their entire crusts are boiling away into gas, replenishing the atmosphere with heavy vapors of titanium oxide, sodium, and vaporized silicates faster than the star can blow them away. Here's the exact detail that makes this discovery so eerie for researchers studying planetary evolution. These worlds were almost certainly not born in the scorched locations where we find them today. If a planet tried to form that close to a young, violent star, the intense heat would have pushed all the dust and gas away before a solid core could ever stick together. Astronomers now know that these planets must have formed much farther out in their solar systems, where temperatures were cool and building materials were plentiful. Over millions of years, gravitational tugs from other passing planets or dense gas disks stole their orbital energy, causing their orbits to slowly decay. The planets were dragged inward along a terrifying spiral path, falling closer and closer toward their stellar executioner. What do you think is more terrifying? A world frozen in total darkness, or an ocean of boiling rock facing a giant sun? Let us know in the comments which extreme environment you find more fascinating, and subscribe if you want to stay updated on our latest deep space breakdowns. As astronomers continued their galactic census, they eventually found the undisputed record holders for the shortest years ever witnessed in human history. One of the most famous is a scorched rocky world named K2 141b, located roughly 200 light-years away in the constellation of Pisces. This extreme super-Earth whips around its host star in just 6.7 hours, meaning it completes nearly 4 full years in a single Earth day. On K2 141b, more than half of the planet is covered in a massive ocean of liquid magma that runs dozens of miles deep. The intense heat of over 5,000 degrees Fahrenheit on the day side literally turns solid cliff faces into gas, creating an entire weather cycle based purely on rock instead of water. The rock evaporates into the sky, travels on supersonic winds to the colder night side, freezes into solid pebbles, and showers down into the magma ocean to repeat the cycle forever. Even more shocking is the discovery of an exoplanet designated as EPIC 246393474b, often called K2 229b. This planet is an ultra-dense iron core orbiting its star every 14 hours, with a composition very similar to our solar system's Mercury, but supercharged on a massive scale. Scientists believe this world used to be a massive gas giant like Neptune, but its star literally burned away all its outer layers, leaving behind only the naked, roasted metal core. Then came the discovery that completely broke all previous records. An exoplanet designated as Swift J1357.2. This system contains a tiny, compact object where material orbits in just 4.4 hours, completing thousands of years every single Earth month. At this distance, the gravitational pull is so fierce that the planet is physically distorted, stretched out from a perfect sphere into the shape of a giant cosmic egg pointing toward the star. Every single measurement taken from these extreme systems tells researchers the same dramatic story. These planets are on a one-way death march. Because they orbit so close to their host stars, they are constantly transferring their orbital energy into the star through powerful gravitational friction known as tidal dissipation. This friction acts like a steady cosmic brake, slowly dragging the planet inward millimeter by millimeter, year after year. This means that right now, as you listen to these worlds are actively spiraling toward their final moments. In astronomical terms, their lifespans are shockingly short, with many expected to survive for only a few tens of millions of years before crossing what physicists call the Roche limit. The Roche limit is the critical distance where a star's tidal gravity becomes stronger than the gravity holding the planet together. When a planet crosses that invisible boundary, the star does not simply swallow it whole in a clean gulp. Instead, the gravity of the star pulls harder on the front side of the planet than on the backside, ripping massive chunks of rock and metal directly out of the planet's crust. Within a matter of weeks, the entire planet is torn into billions of glowing fragments, forming a massive glowing ring of debris around the star. Over time, that glowing ring of pulverized rock slowly spirals into the star's outer atmosphere, where the star completely consumes the remains of the world. By analyzing the chemical makeup of ancient stars, astronomers have actually found high concentrations of iron, silicon, and heavy metals on their surfaces. This provides undeniable proof that many stars throughout our galaxy have eaten dozens of their own planets over billions of years. Scientists are now using the most advanced telescopes ever constructed to study what happens during these final planetary death spirals in real time. In 2023, astronomers using the Gemini South Observatory in Chile caught a dying star in the act of swallowing an entire planet whole, watching the star suddenly brighten by a factor of 100 as it digested the world. It was the very first time humanity had ever directly observed a planet being engulfed by its star. If you could witness the death of an entire planet from a safe distance in space, would you watch it happen? Tell us your thoughts in the comments below, and don't forget to hit like and subscribe so you never miss another thrilling cosmic event. To really appreciate how truly extreme these ultra-short period planets are, we have to compare their internal structures to the planets we know best. On Earth, our world is built in distinct layers: a thin, solid crust on top, a thick mantle of dense rock underneath, and a heavy core of molten iron and nickel at the center. This layered design allows our planet to maintain a steady magnetic field, which shields our atmosphere from dangerous solar radiation and keeps our oceans from evaporating into space. On an ultra-short period world, this delicate internal balance is completely ruined by relentless tidal heating. As the planet travels along its tight orbit, the star's gravity squeezes and stretches the planet's interior like a piece of dough. This continuous squeezing creates an enormous amount of friction deep inside the core, generating internal heat that melts the mantle from the inside out. As a result, these planets do not have solid ground like Earth or Mars. Instead, their surfaces are constantly churning with intense volcanic activity that makes the most violent volcanoes on Earth look completely harmless. Thousands of active volcanic fissures tear through the crust every single hour, spewing superheated gases and liquid metal directly onto the surface. This constant volcanic eruption creates a surface that is constantly renewing itself. Any mountains or valleys that form are quickly melted back down into the churning sea of lava within a few thousand years. The geology of these planets does not move on a slow scale of millions of years like it does on Earth. It changes on a daily and weekly basis. Astronomers studying these extreme volcanic worlds have discovered that some of them are so dense that they must be composed almost entirely of pure metal. For example, a planet cataloged as Kepler 10b, located over 500 light-years away, has a density so high that scientists believe its iron core makes up more than 80% of its total mass. It is essentially a giant cannonball of solid metal flying through the fire of its host star. When you have a planet made mostly of iron moving at supersonic speeds through a star's magnetic field, another wild physical reaction occurs. The moving metal core acts like a massive cosmic electrical generator, producing electrical currents that carry billions of amperes of power. These electric currents run between the planet and the star, creating massive glowing arcs of plasma that bridge the empty space between them. Imagine looking up into the sky from the dark side of one of these worlds and seeing a blinding, crackling bridge of pure electrical lightning stretching from your horizon all the way into the blazing surface of the star. It is a spectacle of raw, untamed energy that completely dwarfs anything we can produce on Earth. These incredible electrical interactions also mean that the planet is slowly eroding from the outside as well as being melted from the inside. The intense electrical currents strip away ions from the planet's upper atmosphere, pulling trails of glowing gas behind the world like the tail of a giant comet. When space telescopes view these planets, they often see a glowing tail of sodium and helium stretching for millions of miles across the star system. Did you know that planets could generate electrical lightning bridges across empty space? Or is this your first time hearing about it? Drop a comment down below with your reaction, and make sure to subscribe so you can keep learning about the deepest mysteries of outer space. The discovery of these fast-moving worlds has also forced astronomers to rethink how solar systems form from giant clouds of gas and dust. Decades ago, the leading theory of planetary formation, called the nebular hypothesis, stated that planets stay roughly where they are born. Rocky planets like Mercury, Venus, Earth, and Mars formed close to the Sun because only rock and metal could stay solid in the heat, while gas giants like Jupiter and Saturn formed far away where ice could survive. However, finding gas giants and massive rocky super-Earths with years lasting only a few hours completely broke this model. It proved that planets do not stay in neat, orderly lanes throughout their lifetimes. Instead, the early stages of a planetary system are a chaotic game of cosmic billiards, where giant worlds slam into each other, push each other off course, and migrate vast distances across space. When a giant planet forms in a thick disk of gas, its gravity creates ripples and waves in the surrounding material. These waves push back against the planet, robbing it of its speed and causing it to spiral inward toward the central star like water circling down a drain. This process, known as planetary migration, explains how worlds that were born in the freezing outer reaches of a solar system end up trapped in blistering orbits just a few hours long. During this violent inward migration, a moving giant planet acts like a cosmic snowplow, clearing out everything in its path. It can easily knock smaller Earth-like planets out of their stable orbits, hurling them directly into the star or kicking them out into the freezing interstellar void as rogue planets. A single migrating planet can completely destroy an entire family of peaceful worlds before finally settling into its own short-period orbit. This realization raises a haunting question about our own solar system's history. Why did Jupiter and Saturn not migrate all the way inward and destroy Earth? Planetary scientists now believe that our solar system was saved by a lucky gravitational dance known as the Grand Tack hypothesis. In this scenario, Jupiter did start migrating inward toward the Sun, but the gravitational pull of Saturn formed behind it and pulled Jupiter back out, saving the inner rocky planets from total destruction. If Saturn had been slightly smaller or formed a few million years later, Jupiter would have continued its march toward the Sun. It would have devoured the young Earth, and today our solar system would consist of a single, scorched giant planet orbiting the Sun in just a few hours. And we exist today only because our giant neighbor planets happen to balance each other out at the exact right moment in cosmic history. Every time we look at an ultra-short period exoplanet, we are looking at an alternate version of our own home, a world where orbital migration went all the way to the extreme limit. These scorched, fast-spinning planets are monuments to the chaotic and dangerous nature of planet formation in our galaxy. If you find it amazing that a single planetary shift saved Earth from being consumed, share this video with a friend who loves science history and hit that subscribe button to keep uncovering these hidden truths. Another fascinating question that researchers are trying to answer is what happens to the weather on a world where a year lasts only a few hours. On Earth, our seasons and weather are driven by our planet's tilt and its slow, steady journey around the Sun. Warm air rises at the equator and moves toward the poles, creating predictable jet streams, ocean currents, and seasonal storms that support life. On an ultra-short period planet, weather operates under rules that seem completely alien to human experience. Because the planet is tidally locked, the spot directly facing the star, called the substellar point, receives a constant, non-stop beam of intense stellar radiation. This spot becomes an eternal hotspot where rock and metal are continuously turned into gas, creating a permanent high-pressure zone that pushes outward in all directions. Meanwhile, the night side of the planet remains at near absolute zero temperatures, creating a permanent low-pressure zone. The extreme pressure difference between the permanent day and permanent night drives supersonic winds across the planet's terminator line, which is the border where daylight meets eternal darkness. These winds can reach speeds of over 5,000 miles per hour, far faster than any storm ever recorded in our solar system. As these supersonic winds carry vaporized minerals across the terminator line into the freezing night side, the vapor rapidly cools and condenses. But instead of forming clouds of water droplets like we have on Earth, the atmosphere forms thick, dark clouds made of liquid iron, silicate glass, and sapphire minerals. These clouds then unleash torrential downpours of molten metal and microscopic glass needles that blast across the barren landscape. Because the planet is completing a full orbit every few hours, the The Coriolis force generated by its rapid movement bends these wind patterns into massive, swirling jet streams that wrap around the equator. This creates a permanent ring of supersonic storms that circulates around the entire planet, transporting heat from the front side to the back side in a desperate, unending attempt to balance the temperature. Using high-resolution spectrographs on modern telescopes, astronomers have actually been able to map these weather patterns from hundreds of light years away. By measuring the slight shifts in light as the planet rotates and orbits, scientists can detect the exact speed of the winds and determine which chemical elements are falling as rain on the night side. They have confirmed that worlds like WASP 76b literally have iron rain falling from their skies every single evening. The physical forces at play on these worlds are so extreme that they challenge our basic definitions of geology, meteorology, and planetary science. They prove that planets are not static balls of rock, but living, dynamic engines capable of producing environments far more exotic than anything found in science fiction. Would you ever want to see a rainstorm of liquid rubies and molten metal through the window of a super-advanced spacecraft? Drop your answer in the comments below, and do not forget to hit the like button if you are enjoying this deep exploration of cosmic weather. This brings us to one of the most exciting frontiers in modern astronomy, the search for the absolute fastest planet that could theoretically exist in our universe. How short can a planetary year actually be before the laws of physics simply forbid it from existing at all? To answer this, scientists have to calculate the balance between orbital speed and the physical density of the planet. If an exoplanet orbits too close to a star, the difference in gravitational pull between the near side and far side of the planet will overcome the planet's own self-gravity. This boundary, known as the fluid Roche limit, depends entirely on how dense the planet is. A fluffy gas giant will be torn apart at a much greater distance than a dense ball of solid iron. Therefore, the fastest possible planets in the universe must be ultra-dense cores made almost entirely of pure iron, nickel, or other heavy elements. Theoretical calculations show that around a normal star like our Sun, the absolute shortest possible orbit for a rocky planet is roughly 3 to 4 hours. Any closer, and the planet would be inside the star's outer atmosphere, where friction would drag it down to its death in a matter of minutes. However, there is a fascinating loophole to this rule that astronomers are currently investigating. Dead stars, known as white dwarfs and neutron stars. White dwarfs are the collapsed cores of dead stars that have shrunk down to the size of Earth, but still contain the mass of an entire sun. Because the star itself is so tiny, an orbiting planet can get vastly closer to the center of gravity without actually touching the star's surface. Around a white dwarf star, a dense metallic planet or the stripped core of a gas giant could theoretically orbit at a distance of just a few 100,000 miles. At that incredible proximity, the planet could complete a full orbital year in less than one single hour. It would whip around the white dwarf at millions of miles per hour, experiencing gravitational forces that bend the fabric of space and time around it. Astronomers have already discovered debris disks and pulverized asteroid fragments orbiting white dwarfs in orbits lasting only a couple of hours, proving that planetary material can survive in these extreme environments. It is only a matter of time before our telescopes spot a fully intact world racing around a dead star in a year that lasts less than 60 minutes. Finding such a planet would provide physicists with an unprecedented laboratory for testing Albert Einstein's general theory of relativity. The intense gravitational waves and time dilation effects produced by a planet moving that fast in a strong gravitational field would allow us to test the fundamental laws of the universe in ways that are impossible to recreate inside any laboratory on Earth. What do you think is the ultimate speed limit for an orbiting world before gravity destroys it completely? Let us know your predictions in the comments, and be sure to subscribe so you're the first to know when astronomers inevitably break the current orbital record. All of these discoveries lead us to a profound realization about the future of our own planet Earth and our place in the cosmic timeline. When we look at these ultra-short period worlds racing toward their deaths, we are not just observing strange alien oddities. We are actually looking at a preview of the distant future of our own solar system. Right now, our sun is in a calm, stable phase of its life called the main sequence, burning hydrogen steadily in its core as it has for the last 4.6 billion years. But stars do not live forever. In about 5 billion years, our sun will exhaust its supply of hydrogen fuel and begin to swell outward, transforming into a massive red giant star. As the sun expands, its glowing outer atmosphere will swallow Mercury and Venus completely, incinerating them in seconds. Eventually, the sun's outer layers will reach all the way out to Earth's current orbit. When that happens, the drag from the solar gas will begin to act like a cosmic brake on our planet, slowly stealing Earth's orbital energy and pulling it inward. Earth's year will begin to shorten rapidly, dropping from 365 days down to months, then to weeks, and finally down to just a few intense hours. Our oceans will boil away, our atmosphere will be stripped into space, and the entire surface of Earth will melt into an ocean of glowing magma, turning our home into an ultra-short period world just like the ones we see in deep space today. Eventually, Earth will cross the sun's Roche limit, and the immense tidal forces will tear our world apart into a glowing ring of rocky debris. That ring will slowly fall into the sun, and every trace of our mountains, oceans, and history will be completely absorbed into the heart of our dying star. The exact same cycle of birth, migration, and destruction that we observe across the galaxy will claim our own home. Understanding these extreme exoplanets is therefore essential for understanding our own origins and our ultimate destiny. They remind us that the universe is not a static museum, but a dynamic, ever-changing environment where worlds are constantly created, transformed, and destroyed by the fundamental forces of gravity and time. Every discovery of a planet with a year that lasts only a few hours expands our knowledge of what is possible in nature. It pushes the boundaries of human imagination and drives our desire to explore beyond the small, safe cradle of our own solar system. The cosmos is filled with countless wonders waiting to be uncovered, each one holding a vital piece of the puzzle of existence. If this deep exploration of worlds with years lasting only a few hours changed how you look at the night sky, please take a moment right now to subscribe to the channel, click the notification bell so you never miss a new video, leave a comment answering what you would name a planet that orbits in 6 hours, and share this video with someone who loves deep space mysteries. Thank you so much for watching, and stay curious until our next journey into the great cosmic unknown.